The NE555 is one of the best-known ICs ever made, and there must be millions of them in the hobbyist market by now. It's been around a long time, and there's a crazy amount of example circuits out there for it. But if you actually look at the datasheet, it's not that complicated. And in this video, I want to show you how it works inside, and how to use it as a timer performing a single action after a specific period of time has elapsed. An oscillator generating a repeating waveform at a specific frequency PWM signal generator, outputting a waveform of varying pulse width for controlling servo motors, LEDs, etc. A PWM signal generator stepping a motor a specific number of steps for a specific period of time. And finally, using two of them together to create a step tone generator like Atari Punk Console. Let's get started. First up, we need to know what the 555 actually is. It's called a PWM signal generator, which means pulse width modulation. It outputs a waveform where the width of each pulse varies according to the value on its input pin. At its most basic, we can use the 555 alone to create a waveform by connecting the output pin to ground through a resistor, and then connecting a capacitor between the output and VCC. By varying the duty cycle of the waveform, we can control the amount of charge stored in the capacitor. If the duty cycle is high, we have a long time for charging, but if the duty cycle is low, we have a short time for charging. This means we can set the capacitor to a specific voltage by adjusting the duty cycle. We can then use this voltage as a reference for other parts of the circuit. In timer mode, we connect a capacitor between the output and ground and set the 555 into PWM mode. Then when the capacitor reaches a certain voltage, the 555 switches off its output transistor, allowing the capacitor to discharge. This restarts the timer and we get a repeating waveform. By setting the resistor and capacitor values, we can control the time between waveform repetitions. This is also known as the period of the waveform. The 555 also has a pin for controlling the waveform repetition rate, and this is known as the PWM frequency, or the clock speed of the waveform. The faster the waveform repeats, the faster the CPU will execute its code. But if we connect the output pin directly to ground, we don't actually get any waveform at all. This is because the output pin is an open drain output, meaning it can only pull the output low. It cannot pull it high. So to get a waveform, we need to add a resistor between the output and VCC, and then connect the capacitor between the output and ground. In this way, the output can go both high and low, and we get a waveform. Now let's look at the 555's pinout and see how each pin works. Pin 1 is the output, and we already know this goes low when the 555 is enabled, and goes high when the 555 is disabled. Pin 2 is the trigger, and when this pin is taken low, the 555 immediately starts its timer. This is useful for starting the 555 at a specific point in your program. Pin 3 is the reset, and when this pin is taken low, the 555 stops its waveform output. This is useful for stopping the waveform when you no longer need it. Pins 4 and 5 are the PWM control pins, and these allow us to adjust the duty cycle of the output waveform. Pins 6 and 7 are the clock inputs, and these allow us to adjust the frequency of the output waveform. Pins 6 and 7 combined gives us a total of 3 clock inputs, which means we can clock the internal oscillator at different frequencies depending on which pin we use. This allows us to generate different waveforms with different frequencies. Pin 8 is the VCC pin, and this is where we connect the positive side of our power supply. Pin 9 is the ground pin, and this is where we connect the negative side of our power supply. Now that we know the ins and outs of the 555, let's look at some examples of how to use it. First up is the Bistable example. Here the 555 is used as a switch outputting either a high or a low waveform, depending on the state of its trigger pin. When the trigger pin is high, it outputs a high waveform, and when the trigger pin is low, it outputs a low waveform. To change states, we need to take the trigger pin low, and the waveform will change after a specific period of time. This is known as the switching time, and it's determined by the values of the resistor and capacitor connected to the 555. With the right values, the waveform will change states after a specific amount of time has elapsed. This makes the 555 ideal for applications where you need to switch between two states after a specific period of time. For example, you could use a 555 to turn on an LED after a specific period of time, or to stop a motor after a specific period of time. Next up is the monostable example. Here the 555 is used as a timer, outputting a single waveform after a specific period of time. To set the length of the waveform, we need to adjust the values of the resistor and capacitor connected to the 555. With the right values, the 555 will output a waveform for a specific amount of time after it's triggered. This makes the 555 ideal for applications where you need to perform a single action after a specific period of time has elapsed. For example, you could use a 555 to turn on an LED for 5 seconds after pressing a button, or to stop a motor after 10 seconds. Next is the Astable example. Here, the 555 is used as an oscillator, outputting a repeating waveform at a specific frequency. To set the frequency of the waveform, we need to adjust the values of the resistor and capacitor connected to the 555, and also the clock speed. With the right values, the 555 will output a waveform at a specific frequency. This makes the 555 ideal for applications where you need to generate a repeating waveform at a specific frequency. For example, you could use a 555 to generate a waveform for controlling a servo motor, or to generate a waveform for stepping a motor. Finally, we have the PWM signal generator. Here the 555 is used to output a waveform of varying pulse width for controlling servo motors, LEDs, etc. The pulse width of the waveform determines the amount of current flowing to the servo motor, LED, etc., and therefore the speed of the servo motor, brightness of the LED, etc. To set the pulse width of the waveform, we need to adjust the values of the duty cycle pins connected to the 555. With the right values, the 555 will output a waveform with a specific pulse width. This makes the 555 ideal for applications where you need to control the speed of a servo motor or the brightness of an LED. And finally, we have two 555s together to create an Atari Punk console. The first 555 is used as a stepped tone generator, outputting a waveform that changes pitch every time it's triggered. The second 555 is used as a PWM signal generator, outputting a waveform that controls the volume of the waveform from the first 555. To create the step tone, we need to adjust the values of the clock pins connected to the first 555. Each time the waveform is triggered, the clock speed increases by a small amount, causing the waveform to change pitch. To control the volume of the waveform, we need to adjust the values of the duty cycle pins connected to the second 555. This creates a waveform that controls the volume of the waveform from the first 555. The result is a waveform that changes pitch and volume every time it's triggered, creating the classic Atari Punk console sound. I hope you found this video useful. If so, please consider supporting me so I can continue making more videos like this in the future. Thanks for watching, and I'll see you next time. Bye.